Okay, welcome to the second lecture on Newton's laws of motion. It's assumed you have seen the previous lecture as I outlined some of the basic techniques we're now going to build on. I'll just very briefly recap some of the previous lectures, but if you're still unsure about some of the terminology and techniques used, I would strongly encourage you to revisit that first lecture. In the first lecture, we defined inertia. Inertia was defined as the resistance of a stationary or a moving body to any change in motion, that's being accelerated or decelerated. And we noted that the bigger the mass of an object, then the bigger the inertia of the object, bigger its resistance to change in motion. To overcome the inertia of a body, we have to apply a force. We looked at the three laws of motion defined by Newton. The first law relates to a situation where a body is in equilibrium. In other words, if you add up all the forces on the body in any direction, they will always equal to zero. So summation of the force equal to zero is the way we denote that mathematically. That relates to an aircraft in steady level flight, for example, where it's moving at constant velocity, but the thrust and the drag are equal and opposite, and the lift force on the wing and the weight of the aircraft are equal and opposite. Don't forget, when we apply Newton's laws of motion, we apply them in a direction because we are considering forces, and forces are vector properties, so they have a magnitude and a direction. Newton's second law of motion states that if you want to accelerate a body, then you have to apply an external force to it. We write the second law mathematically as the summation of all the forces is equal to mass times acceleration, and the force applied is proportional to the acceleration. The third law of Newton's states that to every force there is an equal and opposite reaction force. In the previous lecture we outlined two different models that we were going to use. One relates to horizontal motion, one relates to vertical motion. So in this case we have externally applied force P that's causing the acceleration of the object, but we do have in this particular case a reactive force from the frictional resistance called attractive force that's opposing the motion. What we do here is apply the law of motion, in this case the second law, and we basically add up all the force on the left-hand side of the equation and we equate them to mass times acceleration. Note that we always draw a free body diagram of all our objects. We have a positive notation on our free body diagram to account for the direction of the vectors, and we simply add up the forces on the left-hand side of the law and equate them to mass times acceleration. So in the diagram above, we've got P is applied in the positive sense of our diagram, and R is applied in a negative sense in our diagram. So on the left-hand side of the second law, we write P minus R is equal to MA. If we want to find the value of P, we would simply add R to both sides to find that P is equal to MA plus R. If we have no frictional resistances, then we ignore the R and the force P applied is simply equal to MA. If we apply Newton's laws of motion in the vertical sense, now we have to consider the weight force that applies vertically downwards. So we still have the same approach to the problem. We draw a free body diagram with all the forces acting on it. We define a sign convention for our positive forces and accelerations. And then we simply apply Newton's second law, adding up all the force on the left-hand side and equating them to mass times acceleration on the right-hand side. But now in this case, because we're considering vertical motion, we now have P minus W minus R. In other words, the P force is going up to our sign convention, but the weight force and the resistance to motion is going downwards. That's why it's minus W minus R in the equation. Again, if we want to rearrange to find force P, we simply add W, add R to both sides of the equation. So those are our basic models. We then consider several exercises that outline the application of those models. Exercise 3 relates to horizontal motion of an aircraft, in this case taxiing across the runway. This was an application of the second law as shown here. We had to find in this case the resisting force to the motion. We had to find what the value of R was in this particular case, given all the other parameters. Exercise 4 was a vertical motion case. We have three different scenarios related to a person in a lift. In the first scenario, the lift was at standstill, so that was a first law problem, as shown here. Summation of all the forces equals to zero. In other words, the force applied from the floor to the man, which we're trying to calculate, was equal to the weight force of the man. In part B of the lift scenario, we were accelerating up at 1 meters per second squared, so that now becomes a Newton's second law of motion. So we add up all the forces and they equal to mass times acceleration. Looking at our sign convention, we have upwards positive, that's the direction of the acceleration. So when we summate our forces on the left-hand side of the equation, it would be P minus W is equal to ma. Putting in the values, we can find the force required to accelerate the man in the lift upwards at 1 meter per second squared. Exercise 4 part C, we have the lift now accelerating down at 1 meter per second squared. Notice here on our free body diagram, I've put the positive notation down in the sense of the acceleration here. So when I summate my forces on the left-hand side of the equation, I now have W minus P is equal to ma. Again, I can rearrange the equation to find the force P required to allow the person in the lift to descend at 1 meter per second squared. And exercise 5 was a more complicated problem. It's a Newton's second law problem because we are accelerating a load vertically upwards. But when we applied Newton's second law to our free body diagram, we found that we had two unknowns in the equation, the force in the cable that the question wanted us to find, and also the acceleration was unknown. However, in the question that we were given kinematic information in that we knew the initial velocity and we knew the final velocity and the distance travelled. So we're able to use an equation of motion to find the acceleration. Once we found the acceleration, we could then go back to our law of motion and we could solve to find the value of P. So those were the exercises we undertook in the first lecture, and if you're unsure about the solutions, I would encourage you to revisit the lecture before reviewing the questions we're going to consider in this lecture. Okay, let's have a look at question 1b. Okay, this is actually not a very PC question. Unfortunately, I don't know where I got this question from now, but we've got a man that has a mass of 70 kilograms and he hangs on the end of a rope, so that's not perhaps an appropriate kind of question really. We've got to find the tension in the rope. I guess going back in history when they were having public hangings, I guess somebody somewhere was responsible for making sure the rope was strong enough to ensure that the person being hung, was hung. So someone perhaps did some calcs back in those days, or to decide what strengths of rope they need, maybe. But that's the object here, is to find the tension in the rope. So sorry, it's not very PC, but anyway, we're just looking at the mechanical principles here. Also, this is a question I remember years ago because I put this question on the board. Basically, I drew this on the board and then I was called out of the room. I don't know why. Now somebody wanted to see me outside, so I stopped there. And when I came back in the room after about 5 minutes or so, I saw this on the board. So I wasn't too impressed at the time, but looking back, it's quite amusing, I suppose. And it's quite a good likeness, really, isn't it? I mean, handsome chap there. A bit more hair there than I've got now. But anyway, that was on the board when I came back. So that's the person, that's the scenario we've got. And that's kind of the free body, if you like. Perhaps I'll draw the free body a bit more clearly here. So this is the free body diagram. We've got this person. It's like me. If it makes you feel happy, I think it's me. I'm going to draw him not too happy here because he's being hung here. And as a free body diagram, what we've got to do is to add all the forces acting on the body. That's what a free body diagram is. So I'm going to call this my free body diagram. So what forces are acting here? And I'm sure you would tell me that weight force is acting, okay? In a gravitational field, so on planet Earth, we've got gravitational field, we would have a weight force acting. That would be the weight force acting down. At the moment on my diagram, it looks like he's plummeting to the centre of the Earth because I've just got one force, and we know he's not. He's actually hanging on the end of the rope there. So we must have an equal and opposite force in this particular case, which is going to be, I call it P for pull in the cable, in the rope there. So it's obviously a first law problem, isn't it? It's a summation of all the forces here. They must equal to 0 because the body is stationary. So I think it's fairly clear to see that the P must equal to W in this case. So P is equal to the weight force, which is mass times gravity. Gravity there, just putting the values in, different colour maybe. The mass is 70 kilograms in the question, so 70, and we always assume G to be 9.81 meters per second squared, so and that equals to 686 newtons. Don't forget newtons is the force unit. Weights and forces are in newtons, so alright, so 686 newtons, there we go. That's a very straightforward question. That's the free body. In fact, when the students wanted me to change the name, instead of a free body diagram, they wanted me to call it a dead body diagram, which I think, again, not very appropriate really, but humour of some students, eh? Anyway, that's the first little problem, okay? Question 2b. Now this is a train on a track you'll see here. This is very much like the exercise 3 that we looked at in the previous lecture, which is the aircraft across the runway. So if you want to use that as your little template, then feel free to do it. It's a different question, but it's the same kind of approach, the same kind of model used here. All right, so let's read the question. Let's see what we've got. Extract the information from the question. So the forward force exerted by a locomotive on a train is 0.5 meganewtons. We need to be careful of that prefix in a moment. We're given that the mass of the train, 310 tons, so you be careful with that. And we've got to calculate the acceleration of the train. But it's got a tractive resistance here, so we need to be careful of the tractive resistance, which is 10 kilonewtons, again a prefix there. Okay, so that's the information we're given. Now, always I encourage you to draw a free body diagram. I'm going to draw a choo-choo train because I like choo-choo trains, so mine's going to be a steam train. No, it's not a steam train, but I just prefer to draw steam trains. Okay, so here's my train. What do we know about it? The first thing we're given is the forward force applied. So be very careful here with the information given. It's 0.5 meganewtons. So the thing is, what does mega stand for? It's a prefix. It stands for 10 to the 6. So you could write that if you wanted to. If I put my P here, that's the force that's applied to the train. And so I'll call it P. So we could write it as 0.5 times 10 to the 6 newtons. If you want to, 0.5 times 10 to the 6 newtons is the force applied. You could, if you wanted to, write it as 500 kilonewtons, 500 times 10 to the 3 newtons, if you prefer that. Mass of the locomotive, I've said on a steam train here, but so the mass is given. It's actually 310 tons in the question. That's a metric ton. So that will be 310 times 10 to the 3 kilograms. We've got to calculate the acceleration. So we know it's accelerating. So let me put my acceleration down here. Say I'm going to make that the positive sense here. I always go to the positive sense. It's my acceleration where possible. So that's the sort of sign convention I'm using. And we've got a tractive resisting force, so I need to put that on my diagram. So resistance, that could be aerodynamic friction, of course. That could be steel tires on the track. So I don't know where it's from. We're not actually specifically told where it's from, but on my resistance to motion here. R is equal to 10 kilonewtons, so 10 multiplied by 10 to the 3. I always take my prefixes off when I'm doing my calculations, so I don't forget them. And that's the information I think we'll find from the question. So now I've got to decide, how do I find, in this case, the acceleration? It's the acceleration that's unknown. Well, it's definitely Newton's second law problem, because it specifically asks us to find the acceleration. So apply Newton's second law here. And I just follow the process we used in the previous examples last week. In last week's lecture, I'm going to follow the process through. We're going to summate all the forces. And we're going to equate them, in this case, to mass times acceleration, because that's what the second law says to do. So we're going to have MA. All I do on the left-hand side is simply add up the forces I've got. And I'm going to use algebraic symbols here. So what forces are applied on my free body diagram? Well, I've got the P force. That's the force that's propelling the train from left to right here, and that's positive up at P. And what's opposing that? I can see R is opposing it, so that will be minus R. P is in the positive sense, it's going from left to right, which is our positive notation here, but the R is going from right to left, so that'll be negative. Any other forces applied in the horizontal direction? No, so that must equal to MA. Again, if we just think for a moment, what do we know, what do we not know? Well, we know the P in this case because that's given in the question. We know the R, that's given in the question. We know the mass given in the question. We don't know the acceleration. So one unknown in one equation, we can find that. So we need a little bit of transposition here to rearrange the equation. So I'm rearranging to find A. I'm simply going to have to divide both sides then by M. M is multiplying the A on the right-hand side, so divide both sides by M. So I can write A as, put my values into the equation, so valuing that on your calculators, see if you compare to my value. My A according to my calculations anyway, I get 1.58, and that's meters per second squared, don't forget, for acceleration. That's my calculation there for the working out the acceleration of the train. But again, if you can see the big picture, there's no difference there between the approach we applied in the previous lecture for exercise 3 and this question 2 here. Very similar approach in both cases. So in question 3b, we've got a car that has a weight of 9,810 newtons. It's accelerated from rest, from zero velocity, to 30 kilometers an hour in 5 seconds. That's what's called kinematic information. So we've got a change in velocity from 0 to 30 kilometers an hour, but be careful with 30 kilometers an hour. We need a conversion there to meters per second, and that's in a time period. So they're not giving us the acceleration, but I think from that information we would be able to find the acceleration using the equation of motion, which is hinted in the question. The tractive resistance to the motion that's given to us, it's told it's constant and it's 600 newtons applied. We've got to calculate the force applied. What's the force required to achieve that motion, that change in velocity? And it does say in the question a bit of a hint there to use an equation of motion from our previous notes. So what I'd like you to do is to have a go at that question first of all. Extract the information from the question, draw a free body diagram, put all the forces on the diagram, decide the law of motion you're going to be used. In this case, decide the equation of motion you're going to need, and see if you can tackle the problem. And let's see what you can do with that solution. Just be careful of the conversions there. You certainly got to deal with the 30 kilometers an hour because we always use meters per second in our calculations. Okay, so we've got to find the force applied to the vehicle to achieve this motion. But of course, we can see the acceleration is unknown. So we're going to have to find the acceleration. Now in the question we're given the car is accelerated from rest, so that's initial velocity u of 0 to a final velocity v, and I've converted the 30 kilometers an hour into meters per second, which hopefully you've done. So we've got the 8.3, it's actually 8.3 recurring meters per second here. Now we're given in the question at that time period is 5 seconds, so the time is equal to 5 seconds. So what we will need is an equation of motion that will allow us to link u, v and t and then find a. And if you go to your formula sheets, you will see there's appropriate equations. So the first thing I'm going to do here, I think, is actually work out my acceleration. On our formula sheet, I think you will find this equation, v is equal to u plus at. We'll need to transpose the equation to find the a, so it will be v minus u divided by t. Putting the values in the 1.6 recurring meters per second squared. So that's my first thing. I need the acceleration. Now I found the acceleration. We know it's accelerating, so we know it's the second law. I'm going to make my positive direction here, my positive sense from left to right, because that's the direction of the acceleration. So that's my positive notation. I'm going to apply my law of motion now. So looking at my free body above, my forces are going to be P minus R. That's the big red arrows there. So P minus R. And that's equal to MA. Okay, let's think of what we know, what we don't know in this particular case then. Just thinking it through. Do we know the P? Well, no, we don't. We're trying to find the P. Do we know the R? We know the R, yes. Do we know the... Do we know the R? Yes, we got the R in the question. Do we know acceleration? It's calculated above, but I can see I don't know the mass at the moment. The mass is unknown here. So I've got to find the mass. Now, how do I find the mass? It's not given in the question, but in the question they have given us the weight of the car. So implicitly we have the mass. I haven't given it explicitly. They've given us the weight. We didn't need the weight in the force balance because we're balancing horizontally and the weight force acts vertically down. So it didn't come into the application of the second law, but we do need to know the weight here because from that we can find the mass. So mass is unknown here. So from our weight force is equal to mass times gravitational acceleration. We're just going to transpose that equation. So my mass is equal to the weight force divided by G. In this case, the weight force is given is 9810, divided that always by 9.81, 1,000 kilograms for the mass. Just putting the numbers into the equation now. We've got everything we need now. We can find, in this case, the force. Rearranging, we get P is equal to MA, and then we add the R in this case. So I'm going to let you do the numbers on that. You should find that the force applied here, knowing now the mass, knowing the acceleration, and given the R in the question, I get 2,266 newtons. That's the full solution there. Okay. It's a difficult topic. If you are sort of struggling a little bit with it, I mean, you have my sympathy really, because I know when I first started this 40 years ago, whenever it was now, I didn't find this easy myself. I didn't really get the hang of it initially. You have to work quite hard to apply Newton's laws of motion. From my experience in industry, I have to say they're not the easiest things to apply in practice. They take a little bit of thinking about. So if you're struggling a bit, then you're in good company, if you like. We all struggle a bit with these things, but the more you do, the more you start to get the hang of them. Now again, what I would like to suggest here is in question 4, you now go back to your exercise from last week, exercise 4 in our first lecture on Newton's laws of motion, and you use that as this template for this, because it's a very similar question. It is different, there are subtleties in the question to be aware of, but it's basically the same approach here, so I'd really like you to have a go at this. So I'll outline question 4b with you. So a lift floor structure is designed to carry 14 passengers, average mass 78 kilograms. That means there's 14 times 78 is the total mass in the lift here. We've got to calculate the force reacted by the floor structure under the following design scenarios. So we've got 3 design scenarios again, as I had before. The first one, part A, is when the lift cage is at standstill. So that'll be Newton's first law. The second scenario, B, is when the lift cage is accelerating upwards at 0.6 meters per second squared. And part C, when the lift cage is accelerating downwards at 1.2 meters per second squared. All part D is really considering is the actual design of the floor structure. We're given that the maximum design floor load for this particular part of the structure is 15 kilonewtons, and that's the maximum load it can take. We've got to find what the minimum factor of safety is going to be for the above 3 scenarios. And what that basically means is, undertake the 3 scenarios, that will give you 3 different forces from the floor structure on the lift here, the passengers in the lift. And to find the minimum factor of safety, you would take the maximum of scenario A, B, and C, maximum load in scenario A, B, and C, and you would divide it into 15. And that would give you what's called the minimum factor of safety. And factor of safety are dimensionless. So I can see it says 1.32 here in the answers. So what they're trying to say there is the design of this lift floor structure is 32% stronger than it needs to be. Got that 32% reserve in the material. So don't worry too much about part D. It's like an add-on to the question. But parts A, B, and C, I would like you to attempt on your own if you would. So again, draw the free bodies in each case and then put the forces on the free bodies. Take all the information in the question. Be careful of any units. And then apply the appropriate law of motion and see where you go from there. Okay, for part A here then. It's going to be a Newton's first law problem, of course, isn't it? Because we've got the lift at standstill, so summation of all the forces, they must equal to 0. If I say, give it a sign convention, let's go upwards positive, then it would be P minus W, in this case, is equal to 0, first law. So obviously the force is equal to W, and the W will be mass times gravitational acceleration. Be careful of the mass here, because it's actually 14 passengers in each one is assumed to have an average mass of 78 kilograms. So that's 14 multiplied by my 78. So show it, that's the mass that we're calculating, and that's times 9.81. I get 10,713 newtons, so it's like 10.7 kilonewtons. Just the answer in the question there. Alright, that's part A. Go straight to part B here. Very similar kind of approach, it's just that we've got the acceleration here. So this is part B. And this is the lift now being accelerated upwards at 0.6 meters per second squared. That will be summation of all the forces equals to ma. So if I say upwards is positive, into my convention, upwards would be P, downwards would be W, still W acting down, and that's equal to ma. Got to find the P as always in the question, so P is equal to ma plus W. Again, I'll let you do the figures. You've got the W from the previous part of the question, you've got the mass, and you've got the acceleration upwards of 0.6 meters per second squared, so you can find P. I'm going to let you do the numbers on this, so according to my value, P is equal to 11.37 kilonewtons. The W is from the previous slide. We've got that one calculated. Question for part C, same kind of scenario, just that we're going down again. So this is part C. Again, I've got my free body diagram. Okay, and this time they're saying that the acceleration is downwards at 1.2 meters per second. So I normally take my positive sense then for my free body diagram to be downwards in this case. So I'll have positive down. You can have positive up, it's not a problem. It just needs to say you have to put the acceleration as negative. And some students just forget that, so that's why I tend not to do it. Okay, so again, you would apply the second law. So summation of all the forces is equal to ma. But this time be careful because the sign convention is saying positive down. So I'd actually write W minus P is equal to ma. And you need to rearrange for P, like we did in last week's lecture. I would add the P to both sides, subtract the ma from both sides. So therefore rearranging the P is equal to the W and then minus the ma. So my value was 9,400, so 9.4 kilonewtons. Lower value. It would be lower because, of course, the lift wants to fall down, so all we're doing is slowing the motion down. Whereas in the previous question, we have to accelerate the lift upwards, so more force required. So to find the minimum factor of safety, so minimum, often we call it FOS, factor of safety. That's equal to the maximum allowable design load, so that's 15 kilonewtons here, but it's newtons, 15,000 newtons. And you simply divide it by the biggest value you've got in the other scenarios, the other design scenarios. And my biggest value I've got is 11,300 newtons is my biggest value, so I simply divide it by that. And that should give me a factor of safety of 1.32-ish, something like that. It gives the engineer then a feel for how strong is the component. If it's 1.32 factor of safety, it's 32% stronger than it needs to be. But of course that means it's 32% heavier than it needs to be. So there's a trade-off between the strength and the weight there. So if it's an aircraft structure, you might be trying to make that a bit lighter if you could. But for a general lift structure where the materials are not really expensive, weight is probably not a big issue. That might be absolutely fine and have that bit of factor of safety. What I would like you to do is have a go at, if you've not really started them, is questions 1F and see how far you can progress here, because it's all to do with Newton's laws of motion. So the first one there, mass 5 kilograms suspended from a string, find the tension in the string. I think you'll realise that's a bit like the hanging person. That's a first law problem. Second question, so your body mass 70 kilograms dragged, and the key here is the dragged across the floor at constant speed. If it's constant speed, that means by definition it's not acceleration. That's actually a first law problem. Question 3, it instantly says accelerating, a mass 2 kilograms accelerated at 12 meters per second squared. So that's a second law problem. So read the questions carefully. Questions 4F, a body experiences a force of 20 newtons and accelerates at 60 meters per second squared. So that's obviously going to be second law problem, and so on. All right, so just read the questions very carefully. If they've got accelerations in them, you're looking at the second law. If they're stationary or they're moving at constant velocity, they're first law problems. So question 8F, I would like you to attempt. You've got a lift cage, it weighs 1 ton, so be careful with that. The tension in the supporting cable is given as 9.5 kilonewtons. That would be the P effectively. You've got to calculate the downwards acceleration of the lift here. So acceleration you need to calculate. Answers given in the right hand side here. So I'd like to have a go at question 8F and question 10F. Again, an unusual context here, but nevertheless the same approach applies. Got a parachutist, has a mass of 100 kilograms, is falling at 1 meter per second. The air resistance is equal to 0.5 kilonewtons at this speed. We've got to calculate the acceleration at this speed. Again, answer given in the bracket. So both second law problems because we're dealing with accelerations there. If anyone wants a bit of fun, I know some of you like a bit of fun, then actually question 9 is for fun. Here you've got a mass supported by a rope, is accelerated at 2.5 meter per second squared. The tension in the rope is given as 12 newtons. You've got to find the mass. Okay, is that all right? We've come to the end of the session there. Please try and have a go at the enrichment. Even if you get the wrong answers, don't worry about it. Just send it over to me and I'll give you some feedback on it if it's not right. But I would like you to have a go at it. They are difficult questions, but if you could try and apply the approach we've been looking at the last couple of weeks, you should be able to make a reasonable attempt at them anyway. So see how far you get with them. Cheers then.